So this is part one of Newman projections. The first part of this video will go through what Newman projections are, what they represent, and then the second part will actually go through the specific steps they would use to draw a Newman projection given a skeletal structure. All right, so before we begin with Newman projections itself, let's review stereochemistry. So for this, I have a drawn structure right here. And we can see that we're using wedges and dashes to represent the different arrangement of the hydrogens in this molecule. And so HC and HF project towards us. HB and HE project away from us because they're dashed. And then these ones highlighted in red are in plane because they're neither wedged nor dashed. And so we know that we have single or free rotation around single bonds. And so we could rotate this middle carbon-carbon bond. And for this, we will keep that first carbon the same. So we didn't change anything about HB, HA, or C. However, what we're going to do is move all of the hydrogens over one spot on that other carbon. So we just shifted them all one carbon or one rotation spot. And so since we have that free rotation, these two structures are equal to each other. They represent the same molecule, but just a different sort of conformational state. And so these two molecules would be two different conformers of the same molecule. And so again, it's the same exact molecule, it's just we rotated around that middle bond. If we were to swap two groups instead, and so here, let's draw a second structure where we're again keeping that first carbon the same. And then what we're doing is we're keeping one in the same position on the right, but then swapping the other two. So instead of rotation, we just kind of swap them. So we'll do HA dashed and HF wedged. So you can see that we just swapped that HA and the HF. These two would not be equal to each other because we didn't just rotate around a bond, we actually swapped that three-dimensional arrangement. And so in another video, we'll go through how those molecules are related. But for the purpose of this video, we're looking at conformers. So we're just looking at what happens when we rotate around the single bonds and how do we represent that using these Newman projections. And so it's important to note that there are no changes to the types of bonds and no electron movement between conformers. All we're doing is rotating that bond. And what we use those Newman projections for is to help visualize what those conformers look like in a kind of a more obvious way than if we were just to draw like the skeletal representation. So let's take the same molecule. So I'll just take the one that we were working with from above and draw out those wedged and dashed hydrogens. And then I'll draw out the Newman projection for this one. And then we'll talk about how to actually draw that out given another structure. So in a Newman projection, what we're doing is we're saying, let's imagine that we're looking down this center bond right here. So the one that I just highlighted in red, we can see that the eye that's drawn, the green eye that's drawn to the left is looking down that bond. And so essentially what we're doing is we're flipping the molecule 90 degrees so that this carbon right here is the front carbon, and I'll label that CF for front. And then this carbon right here is the back carbon. And when we convert it to a Newman projection, we draw a circle to represent that entire bond. And then in that circle, this dot in the middle represents that carbon bond, where the dot in the front is that carbon front. And then we can imagine that there's a dot on the back of the circle, which would be carbon B. And so from here, each of those carbons has three groups. So a Newman projection will always have three groups from the front carbon, and then three in the back. And then again, in the upcoming steps, we'll talk about exactly how to fill these in. But we can see that that when we fill in the different carbons, we end up, or the different groups on the carbons, we have the three groups on the front and then the 3 in the back. And so here I'll highlight the groups in the front. So those are going to be those green ones. And so we can see that they're all bonded to the same carbon, or CF. And then we can do the same thing with these orange ones, HD, HF, and HE, which are bonded to that carbon. And so in this state, it's a lot easier to see potential clashes. So if we had like different groups, not just hydrogens, we could see potential steric clash. And then in the next videos, we'll talk about what that steric clash represents and how that relates to the energy or torsional strain that a molecule represents. So this video won't go through that. We'll do that in the next video. All right, so let's go through the actual steps of how to take a skeletal structure and convert it to a Newman projection. So for this, I'm just going to work with this structure right here for all of these. And what we're asked to do is to draw the Newman projection given this I from the left side of the molecule going down this carbon-carbon bond in the middle. All right, so the first thing we want to do is to draw in all the missing hydrogens and then identify what the 3 substituents are for each carbon. So we have the front carbon right here and the back carbon right here. I'm going to make this a little bit bigger so we can actually draw in the hydrogens. So here we know that we're missing a hydrogen here. So I'll label that HA. We also know that we're missing this HB. That's dashed. And on the other side, we're missing a wedge group. So we know that we have a wedged HC here. And so altogether, we know that the front carbon has 2 hydrogens and a methyl group. So HA, HB, and a methyl group. And then that back carbon has a HC, a methyl group, and chlorine. And just to help differentiate the different hydrogens, I'm going to label them HA, HB, and HC. For your class, you likely don't have to do this. You could probably just label them all as H. All right, the next thing that we're going to do is identify which, for step 2, we're going to identify which substituents lie in plane with the indicated CC bond. So for this, I'm going to copy over what we're working with above. And the way that we identify what's in plane is it's going to be everything that isn't dashed or wedged. And so we can see that the carbon front and carbon back are in plane, and then HA is in plane, and then this chlorine is in plane. And so again, we know this because these are the groups that are not dashed or wedged. All right, next we want to determine if the molecule is in staggered or eclipsed state. And so in the next video, we'll talk more about what these states represent. But for now, what we want to identify is that staggered has the in-plane groups on the same side of the carbon-carbon bond. Or sorry, staggered has in-plane groups on opposite side. On opposite side of carbon front, carbon back bond, and eclipse will be opposite. And so if we take a look at this molecule that we have up here, we can see that those red lines representing the chlorine and the HA are on opposite sides. of that CF-CB bond. And so that means that this will be in the staggered state. All right, next we want to draw the appropriate Newman projection that's empty. So we're not going to fill in groups yet. We're just going to draw that empty circle. And so there are 4 different options for an empty Newman projection. So I'll draw all 4 right now and talk about those differences. All right, so in this first one, we're going to have a staggered state. Next, we're going to have an eclipse state. All right. Okay, so we can see that the 2 staggered states, which are the first and the third, have lines that don't line up with each other. So the front carbon, the lines coming from that front carbon and the lines coming from the back carbon are not like directly parallel to each other. While the ones that are eclipsed, which are the second and the fourth, have lines that kind of like parallel each other. So we can see that the front and the back carbon of both of those have lines that line up with each other. The next difference between these is dependent on whether that first line from the front carbon is pointed up or down. So I'll highlight those here. So in the first 2, that bond is pointed up, while in those second 2, that bond is pointed down. And so to determine which one is appropriate, we have to look at our skeletal structure. And so we can see that in our skeletal structure, on this front carbon, this HA points up. And so that means that we have to choose one of these 2, one of the first 2, since we want that line to be pointed up. The other thing we have to identify is whether it's staggered or eclipsed, which you already did in step 3. And so we know that since it's staggered, our correct Newman projection is going to be this one. And again, you're always going to choose one of these 4 Newman projections. There's no other situation in which you'd have like a different one. These are the only 4 empty projections that you should be using. And again, this is the correct one because HA points up and we're in the staggered state. All right, next we want to fill in the empty groups. So we're going to take our empty projection, copy it over here, make that a little bit bigger. And what we want to do is take our molecule from up here, and I'll copy that over too, just so we can keep track of all the groups. And we want to take those highlighted red molecules or atoms and fill them in. So we know that HA is bonded to that front carbon. So HA will be pointed up, which means that that chlorine, which is on the opposite side of HA, is going to be directly opposite, bonded to the back carbon. And so we now filled in our HA and chlorine. And so now we can kind of imagine that those red highlighted lines in our molecule represent that red highlighted part of the structure in the skeletal state. And we can also just double check that we've correctly chosen our structure because we can see that the HA and the chlorine are opposite each other, which is exactly what we get in our Newman projection. All right, next we want to fill in the rest of the groups based off the perspective. And this part is a little bit trickier. There's not really like a set of rules that you can directly follow. It's more so just kind of visualizing it. And if you have a molecular modeling kit, it might help to do this. But if we recall from what we're doing, we're kind of taking this bond down the middle and rotating it to face us. And so if we rotate that bond, we can imagine that that HC group or that wedged group ends up being on the right side of the molecule. And so we can fill in HC to be on the right side and HB would be on the left. Oh, sorry, that's a methyl group. That just be a methyl group. So we'll just put Me here to represent that. And then we also know that HC on the other carbon is also going to be on the right side. So all wedge groups should always be on the same side of the molecule. And all dash groups should always be on the same side of the molecule. And so we have this front methyl that I'll highlight in green. And HB, which end up being bonded to the front carbon. And then we have HC in the methyl group in the back. Okay. And as I said before, all wedge groups, so the two wedge groups that you should have should be on the same side of the molecules or of the projection. And so in this case, the two wedge groups are that methyl group and the HC, which we can see are both on the right side here. All right, in the next video, we'll go through what exactly is the difference between eclipse and staggered states and what that means for the strain that a molecule experiences. And then we'll also do some practice problems related to filling out a Newman projection given the different states.